We've just seen several examples of how objects in both kinematics and dynamics can act as if all of their mass is concentrated at a particular point. That particular point is called the center of mass. It's the location at which all of the mass of an object may be considered for the purposes of linear or translational motion. We'll see coming up how the center of mass is sometimes called the balance point and why that is. But let's define it further. Let's do a little example. Can you find the center of mass intuitively for these objects? Usually you think about the symmetry of the object, and the center of mass is typically in the middle of that. So for instance, for this long rod, it's right in the middle of the length. For a circle, it's in the middle of the circle. Same thing for any of these geometric shapes. One problem with this is that you're automatically assuming, because I use the same color for the shape, that it's made out of the same material. So you made an assumption that the density of the mass inside of these objects is constant over the volume of the object. This may or may not be true. For items where it is true, such as a ruler or a plate, a dinner plate, finding the center of mass is pretty straightforward because you can just use symmetries of the situation in order to figure out where it is. Let's define it mathematically, though, based on that intuition that we just had and this idea that it does depend on the density. We can say that the center of mass, let's just say for the x direction, is the sum of the mass of a particle times the location of that particle, and you sum over all of the particles I, and that's divided by the total mass of the particle. If the particles are discrete, you can say m1, which is the mass of particle 1, times the position of particle 1, and then add that to particle 2, particle 3, so on and so forth for all of the particles that you have. Divide that by the total mass of the system. Same thing happens in both y and z, and you can do this for all 3 dimensions and figure out where the center of mass is for each one. That's all well and good, but it's a little confusing. Let's dissect what it means a little bit more. First, let's examine units. If we look at the top, we know that we can only add things that have the same units. That's fine. Each of the parts on the top are a mass times a distance, and those are all being added together, and so that works. So the units on top are the units for mass times the units for distance. In the denominator, we're just summing up the masses, so the units must just be mass. We can write that as the numerator having units of kilogram meters and the denominator having units of kilograms, which the kilograms cancel from the top and bottom, giving us just meters for the units. Does this make sense? It's supposed to be a position where all of the mass is concentrated. It makes sense for that position to be measured in meters. It's a distance. If we want to calculate this out, it can be a little confusing because if you think of like a meter stick, you kind of intuitively know that the middle of the meter stick is where the center of mass is, and yet how do you apply this equation to that? So the first thing you have to do is put whatever it is on some kind of coordinate axis. So in this case, we're going to choose the coordinate axis. This is going to be a 28 centimeter ruler. I don't know why I have a 28 centimeter ruler, but that doesn't matter. And we're going to put it on the coordinate axis so that one end of the ruler is at the origin. And we're going to just think about the x component. We can break up this ruler into 28 1 centimeter by 1 centimeter segments. And if we know the mass of each of these segments, assuming that it's constant throughout, let's just say that it's each 1 centimeter by 1 centimeter chunk is 1 gram. So each one of those green boxes that I put up is a chunk. Each one is 1 centimeter by 1 centimeter, and they each weigh 1 gram. Now we can use this equation. We can plug into the numerator. The first chunk, M1, has a mass of 1 gram. That's fine, they all do. The location of the first chunk, we're just going to talk about where the center of the chunk is, assuming it's a small enough segment. And it's only 1 centimeter big, so the center of it is going to be at a half a centimeter. Chunk 2, same thing. It's 1 centimeter moved over, so its location is 1.5 centimeters, so on and so on and so on, until the 28th chunk, which is located at 27.5 centimeters. Adding all of those together gives us the numerator. The denominator is just the total mass, so we just add 1 gram up 28 times. I'm going to simplify this a little bit because I can look at this system. I know that every single part on the numerator has 1 gram. I can factor that out. And now I'm just adding up all of these distances. If you think about, look at the first one, which is 0.5, and the last one, which is 27.5, they add up to 28. If you do the same thing for the second mass and the second to last mass, they also add up to 28, and so on and so forth. And there's 14 of those pairs. So I'm going to simplify the bottom a little bit by saying that I pulled out that 1 gram. There's 20, each one of those 14 segments that we add, the first and the last, the second to last, the third and the third to last. Each one of them adds up to a length of 28 centimeters, and there's 14 of those. On the denominator, there's just 28 segments that each have 1 gram, and so we're able to put the 1 gram times 28 on the bottom. Now we can see that we can easily cancel the 1 gram from the top and the bottom. We can cancel the 28 from the top and the bottom, and we're left with 14 centimeters. 14 centimeters is exactly in the middle, so your intuition about this ruler and where the center of mass would be right in the middle at 14 centimeters is correct.